Welcome to this WACE Academy online lesson where we will be exploring the topic of geometric sequences. This lesson will cover and expand upon syllabus dot points 3.2.5 to 3.2.8. From the previous video, we know that arithmetic sequences are a series of numbers that have a constant value being added or subtracted between consecutive terms. But what if there was a different relationship between terms? What else can we do to a term to produce the next? Well, in geometric sequences, the answer is we multiply or divide to get to the new term. Some simple geometric sequences are 2, 4, 8, 16, or 10, 100, 1000, 10,000. Here it is simple to see what we are multiplying by to get to each new term, 2 and 10 respectively. But what about some slightly harder sequences? 40, 20, 10, 5. Here we divide by 2, which can also be considered as multiplying by 0.5 each time. Another could be 50, 10, 2, 0.4. And with this sequence we are dividing by 5, which again can alternatively be considered as multiplying by 0.2. We can keep going to make it slightly harder. This time, 24, 36, 54, 81. Upon inspection, there is no obvious number that we are multiplying or dividing by to progress through the sequence, but we can calculate this value, which we call the common ratio, written as R, by dividing any term other than the first by the previous term. Note the reason we can't choose the first term is because there is no term before it to divide by. Here we can take the third term, 54, and divide it by the second term, 36, which gives us 3 over 2, or 1.5. So this is the common ratio. R is equal to 1.5. Ensure not to confuse common ratio and common difference. Arithmetic sequences have a common difference because we are adding or subtracting between terms, while geometric sequences have common ratios because we are multiplying or dividing between terms. A method I used to remember which was that A for arithmetic comes first in the alphabet, and we learn arithmetic sequences before we learn geometric because they are easier. Just as we have with arithmetic sequences, there is also a geometric recursive formula that allows us to calculate the next term if we know the previous term, which we call the geometric recursive rule. It can be written as Tn is equal to Tn take 1 multiplied by R, with T1 equal to some value. So as we can see, unlike with our arithmetic recursive rule, where we added or subtracted a value to Tn take 1 to find Tn, we are now working with geometric sequences, so we'll be multiplying or dividing Tn take 1 by R to find Tn. In the previous example, we had the sequence 24, 36, 54, 81, and so on. If we were asked to find the fifth term, when using the geometric recursive rule, the equation will be T5 is equal to Tn take 1 multiplied by R. Substitute in 5 for n. 81 is T4, which when multiplied by 1.5 gives us 121.5. So T5 is equal to 121.5. But what do we do if we are asked to find a term and we do not know the previous term? For example, we have the sequence 1, 3, 9, 27, 81, and we are asked to find the 12th term. We could continue the series by finding R until we reach the 12th term, but this is impractical. In order to do this, we need to know the general geometric rule, written as Tn is equal to T1 multiplied by R to the power of n minus 1. As you can see, this requires us knowing or being able to find n, T1, and R. I'll show you in a second how this formula works, but first let's find R. Using the second and third terms, 3 and 9, 9 divided by 3 is 3, so R is equal to 3. So now back to our formula. We know that T1 is equal to 1, T2 is equal to 1 multiplied by 3, T3 is equal to 1 multiplied by 3 by 3, T4 is equal to 1 multiplied by 3 by 3 by 3, and T5 is equal to 1 multiplied by 3 by 3 by 3 by 3. You've probably noticed a pattern occurring here, which we can use to shorten the equations. T1 is equal to 1, T2 is equal to 1 multiplied by 3, T3 is equal to 1 multiplied by 3 squared, T4 is equal to 1 multiplied by 3 cubed, and T5 is equal to 1 multiplied by 3 to the power of 4. So to generalize this, Tn is equal to the first value in the series, or T1, multiplied by r to the power of 1 less than the number of terms there are, n minus 1. So, Tn is equal to T1 multiplied by r to the power of n minus 1. Note T1 can also be represented by the letter A. If you get this in a question, just pretend A is T1. Now to find the 12th term of our series. We know that the first term was 1, so T1 is equal to 1. The common ratio, or r, is 3, and we'll substitute 12 for n into the formula. So, T12 is equal to 1 multiplied by 3 to the power of 12 minus 1. Now we know the basics of what geometric sequences are and how to find their terms, we can begin to apply them to real life and where these things actually exist. Geometric sequences can be modelled on graphs to display exponential growth and decay. Let's say Pete has $40 in his bank account, which earns 8% per annum of interest compounded yearly. To turn this into a geometric recursive rule, we need to find some values first. T1 is the first term in the series, so T1 is 40 because that's Pete's starting balance. We know each year the amount in his account increases by a ratio of 1.08, or in other words, 8% of his balance is added on top of the original sum, so R is equal to 1.08. T2 represents Pete's balance at the end of the first year and can be calculated using the recursive rule. T2 is equal to T1 multiplied by 1.08, which is equal to 40 multiplied by 1.08, which is equal to 43.2. So at the end of the first year, Pete will have $43.2 in his bank account. At the end of the second year, T3, Pete will have $46.66 in his account. At the end of the third year, T4, Pete will now have $50.39 in his account. And finally, after 4 years, he will have $54.41. Notice at the end of each year, Pete's account is increasing more rapidly. By drawing this on a graph, we can see this pattern reflects an exponential function. Now you're ready to look at some sample WACE questions. Question 1. A student was monitoring the population of flies, P, in a container. He counted the flies every afternoon at the same time. He found the population increase according to the rule. P is equal to 100 multiplied by 1.1 to the power of t minus 1. Where t was the number of days he had been counting for. Part I asks us to complete the next 2 rows of the table. Finish reading the rest of the question for yourself and pause the video to see if you can finish the question. The first part asks us to complete the table. This involves identifying the correct equation to use along with the values to substitute into it. Here we will use the formula for population given to us. The third row will be after 3 days, so we'll substitute t for 3. 100 multiplied by 1.1 multiplied by 1.1, which gives us 121, rounded to the nearest whole unit. The fourth row is pretty much the same, but it is a day later, so t is 4. The calculation will be 100 multiplied by 1.1 multiplied by 1.1 multiplied by 1.1, rounded to the nearest whole unit, because you can only have whole flies. Part II gives us a value for t, 2 weeks. But in the formula we're given for the population of flies, time is measured in days, so we'll have to convert weeks to days, so t is equal to 14. The question asks us for the number of new flies, so firstly we'll find the population at 14 days. Putting 14 into the formula, p is equal to 100 multiplied by 1.1 to the power of 14 minus 1, 345 flies. Next we have to find the number of flies on day 1. This is given in the question, but this is how you could find it mathematically. T is equal to 1 because it's the first day, and anything to the power of 0 is 1, so 100 times 1 is 100 flies, which is the same amount given to us in the question. The amount of new flies is the population at day 14 minus the population at day 1. 345 minus 100 is 245 new flies. Finally, Part III wants us to find the rate at which the population of flies is increasing per unit of time. There are 2 ways of finding this. Firstly, we can see from the formula, for every new day the previous population is multiplied by 1.1, which is an increase of 0.1 or 10% per day. Alternatively, we can take two consecutive population values, such as at days 1 and 2, 100 and 110 flies, and find the increase, 10 flies. Then using our percentage formula, find what 10 is of 100, which again is 10%. So the rate of population growth is 10% per day. That brings us to the end of the lesson. I hope it was helpful. Please leave any questions in the comments section and we'll get back to you with an answer.